In this section, we're going to talk about time. And time is related to astronomy because our fundamental unit of time in physics is a second. But where does a second come from? Well, if you think back to originally when people were measuring time, the most logical way to measure time is by measuring the passing of a day and then a night. And time is kind of something that's hard to define. Everybody knows what time is, but if you ask for a definition of it, it's hard to come up with a definition. Mostly people say it's the interval between successive events. So it's the interval between sunrise and the next sunrise. Okay? And so to ancient people, time was always measured by the days, and it was usually either sunset or sunrise, because those were well-determined things that they could see. Nowadays, we start our days at midnight, but to the ancient people, they had no idea when midnight occurred. They didn't have clocks. And so time was measured mostly by sunrise or sunset. And then it started to become where the ship's captains we talked about started using the meridian point of the sun, or they used noon and what they called local noon to determine time. All right. So if the fundamental unit was a day, then a day was then split into 24 hours, and each of those hours into 60 minutes, 60 seconds, which we got from the Egyptians. And then that second became our fundamental unit of time. All right, so we already talked about the fact that the Earth is spinning around here, like this. And we talk about a day as being the fundamental unit. But we have different kinds of days. We have what we call a solar day and a sidereal day. A sidereal day is a day measured by the stars. And the solar day is measured by the sun. So if we use it as noon, so here is the Earth, here's the North Pole sticking out of the Earth, and we already realized that the Earth, or is it arrow, is spinning in a counterclockwise direction. And so to measure a solar day, you just measure the interval of time between when the sun is on the meridian until it rotates around and the sun is back on the meridian again. One day later, we define that as 24 hours. So a solar day is 24 hours. Now, sidereal day says, instead of measuring it by the sun, we're going to measure it by a star. And so we're going to look when a star, if I'm facing south and the star's in the meridian, it rotates around, comes back up, and when the star hits the meridian again, that's one sidereal day. Now the question is a solar day and a sidereal day the same amount of time? If you measure the rotation of the Earth by the sun or by the stars, would it change? Now we know the rotation of the Earth is not changing, at least on a very small time scale, it's not changing. It is changing, the Earth is slowing down. But it's slowing down at the order of a few seconds every million years. So it's a very tiny effect. Oh. But it does have to be taken into account if you're trying to be super precise. But a sidereal day is measured by the stars. Well, if it takes 24 hours for the Earth to go around, shouldn't both these be 24 hours? Well, that is not the case. What happens is what we're going to do is I'm going to put the sun over here. Remember, this is not the scale, the sun's way out there somewhere. When our astronomer Herb is right here, so the sun is directly over his head. Then we call this noon, right? But while this is spinning around, while the Earth is rotating, like this, then Herb will rotate around once till the sun is back over his head. That's a solar day. However, while the Earth is rotating, it's also revolving. So by the time Herb comes around 24 hours later, the Earth is not here anymore. The Earth has moved forward in its orbit because remember the Earth is revolving around the Sun. It's gone about 1/365th of the way around, or about 1 degree. So it's moved forward 1 degree. So the Earth will be here. And then Herb, now our Herb, will be here, so he's gone around exactly 360 degrees, but it's not pointing towards the Sun anymore. He has to rotate actually about 1 degree further so that the Sun is directly over his head. I know that might be a little bit complicated, but think of it this way. If you're spinning around, so imagine that the Earth globe over there is actually the Sun. As I spin around, that would be 1 day, but as I'm spinning, I'm stepping forward, I'm facing that way, but the Sun is over here. I have to rotate a little bit further. Okay? So that means that a sidereal day is slightly shorter than a solar day. In fact, a sidereal day is 23 hours, 56 minutes long. Or the difference is about exactly 4 minutes a day. Close to 4 minutes a day. Okay? All right. What that means is that stars will rise 4 minutes earlier every night. So you could have a homework problem that says something like this. What time will the star Sirius rise in 12 days if it currently rises at 12:15 a.m. Question. All right. Well, to do this, all we have to do is know that the difference every day, the star is going to gain 4 minutes. So 4 minutes every day for 12 days. So all I do is say, okay, 4 minutes per day. I multiply that by the number of days. In this case, it's 12 days. And so 4 times 12 is 48 minutes. Now you got to be careful here. Remember, it's always 48 minutes earlier. So it gets earlier all year long. And so all I do is take what time it currently rose at 12:15 a.m. and I'm going to subtract 48 minutes. Okay. Now, this is where it gets a little tricky because time is not a base 10 system, it's a base 60 system. Okay? So, when I subtract and I borrow from here, I'm going to borrow 0 from here, this becomes 15. 15 minus 8 is 7. But then I can't take 4 from 0, I have to borrow 1 from here. This becomes 11, but when I borrow 6. I don't borrow a 10, I borrow a 6. Because I'm borrowing 60 minutes, essentially. And then 6 minus 4 is 2, and I end up at 11:27, and I switch from AM to PM. So the hardest part of doing this problem is not figuring out 4 minutes a day, it's subtracting with the weird time system. Okay? So that's the easiest, or that's the way you have to do it. Remember, when you borrow from the hours, you have to borrow 60 minutes, and it's not a 10. But that's true for all stars. They're all going to rise 4 minutes earlier day. Now, if we do this for a whole month of 30 days, What's 4 times 30? So in 1 month, by the way, that was the answer to the problem. In 1 month, you have 30 days. What's 30 times 4 is 120 minutes. So in 1 month, it rises 2 hours earlier. How many months are there? 12 months. 12 times 2 hours is 24 hours. So exactly 1 year later, when we're back in the same position, the star is going to rise at that same time 1 year later. But then it's going to rise 4 minutes earlier. In fact, if you took 24 hours and divided it by 365, guess what? You get 4 minutes. That's why it ends up being 4 minutes, and there's a 4-minute difference between a solar day and a sidereal day. All right. Let's talk about time zones. Time zones, because that's currently how we do time nowadays, is you do time zones. Everybody in a certain region of the earth has the same time. That's why it's called the time zone. And this occurred back when they started to have trains. And trains were taking people from one place to the other. And you wanted to know what time the train was going to get there, what time it was going to depart. Up until then, people would move around while they were just moving by horses or walking, and nobody really cared about the time. Farmers would get up, and 90% of the people were farmers, would get up in the morning with the sun, go to bed when the sun went down. And it wasn't until we started to have trains and then the Industrial Revolution that they started worrying about time zones. And the idea is the Earth can be split